Okay, let's get started. So today we are doing the rendering pipeline, which is this option here, rendering pipeline in the lectures directory of the bhacker.com website. So I'm going to minimize this and start the presentation. So this one is going to put the pieces together from some of the previous lectures you've had. It applies towards VRML and OpenGL and graphics in general. So it's a general computer graphics foundational kind of lecture that is going to get into the concept of the pipeline in terms of the rendering process for computer graphics. And it's the classical sequence that you're going to be introduced to today. Talked about the concept of rendering already, but just to refresh your memory, rendering is the process of taking that three-dimensional model and producing it into a single two-dimensional picture, because our graphic displays are still two-dimensional. So we have to render it to a two-dimensional display in order to make it present itself in a three-dimensional kind of fashion. So it's kind of an interesting process. The rendering is the translation. So there's a process that gets followed. So the classic rendering approach approaches all work with polygons and triangles in particular. So we're still looking at a polygon level of translation, which is why we're concerned with polygons to begin with. And if we look at the wireframing lecture, probably won't do that one for a couple weeks. That one works with the concept of creating the polygons to get them into the rendering process. So today we're focusing on the rendering process. It doesn't include creating the 3D models. That's modeling. So the other lecture I gave you a couple weeks ago, because last week we really didn't have a class, but a couple weeks ago we started talking, or I started finishing talking about modeling, and the 3D model, 2D model, the modeling plane, the XYZ coordinates, matrix translations from one location to another, rotation, although there's different concepts. That falls into the modeling category. And it also does not include movement of the models or animation, artificial intelligence or physics in terms of that component. So probably going to hit animation coming up soon as well. So it's another important concept of computer graphics to consider. So by definition, we want to look at the concept of the pipeline. So what is the pipeline? It's the classic rendering that is done as a pipeline. Think of it like an assembly line. We are going to decompose something, represent the data in a better way that's more compatible with the display in the graphics card, and then translate it and then shoot it out the other end and make it into something that's going to be viewable. So triangles travel from stage to stage as they get translated into the image. At any point in time, there are triangles at all stages of processing. So it happens in, like I was saying before, sort of an assembly line, if you're familiar with that term, where in different stages the end product is translated or transforms. So by the time something ends up at the end, and it's the triangles that are ending up at the end, they're already in a two-dimensional kind of state. Can obtain better throughput with a pipeline, and much of the pipeline is now in hardware, where it's actually supported by hardware if it's not in hardware itself. When we talk about hardware, we talk about graphics cards. So the graphic card is actually doing this. The GPU, the graphics processing unit on the graphics card, is the power behind the pipeline. It's where the pipeline is actually getting its cycles from in terms of its processing. So it starts with the model space that we're creating, and then we have the model and the view transformations that give us our view space, that provide with projections that give us our normalizing for our device space. So at this point we're looking at where is our output device, and our device space is going to be our monitor in most cases if we're looking at computer screens. And then we have the viewpoint mapping, and then we have the screen space. So we're taking the model space and translating it into the screen space. Long story short, it's not one process. It would be great if it would be just one translation, and instead, actually, if you're looking at a flat image, there's no translation. You just put it out there on the screen. But a rendering pipeline for computer graphics is taking that three-dimensional plane and figuring out from the model space. We talked about model space last time, I believe. Considering the views, the translation calculations or the rotation calculations, and all those different components that we've put into the model, defining the view space from that, which is part done by hardware, part done by programmer, because the programmer is defining the view, is representing the view in terms of its perspective. Sending it through and creating the projection out of that. The projection is going to give us our device space normalization. So the normalized is referred to as normalization, which is the concept of taking it and making it compatible. So you're taking the view space and you're making it fit into the device space. Compatibility, and it's really referred to as normalization, normaling. And then that view mapping simply takes it and projects it out onto the view screen, or the view space. And then this is the information that gets populated on the monitor as we see it. So it's a lot of calculations that are existing throughout the classic rendering pipeline, and it can be broken down into different stages with different algorithms and different hardware supports for each stage. The whole thing can be optimized by putting it 100% into hardware, making it run from the chips instead of the algorithms. Because the algorithms are going to give you, and what I'm going to do in the next few minutes here is go over each one of these different items in a little bit more detail. These are the phases or the stages of, it's not really compilation, but it's very similar to compilation that we get in classical programming languages. So we're compiling, if you think about it, the model space into the screen space. And we're creating that representation. And it's going to be readable. And as I was saying before, it can be optimized by putting it into hardware. Not a requirement, but definitely provides more optimization in terms of speed. Because if you think about this concept, there's a lot of data, there's a lot of data manipulation, a lot of storage, a lot of temp memory. It's memory intensive. So people who don't have graphic cards, like really powerful graphic cards, either this is not going to work, or it's going to take a very long time because the software has to do it. So you speed up the system by actually putting in a graphics GPU processor and a graphics card that has the pipeline essentially built into the card, so the information can be translated through the hardware, and it's much faster. And it's basically just running a routine or an algorithm to do all of this changes that are going to be needed throughout the different spaces. Phases, I meant to say. So model space. What's a model space? A model space is the coordinate system that's attached to the specific model that contains the triangles. We talked about the model space, I believe, in the last lecture or the lecture before. It's the definition of the space that's inside of the frame or the window. It encompasses all of it. It's the easiest to define model in its local coordinate system. It's the XYZ coordinate system, the space in which the model and everything's going to exist. Separation of the object design from the world location. And multiple instances of an object might actually appear in the object space, the model space, I should say. And hopefully you have more than one object in the model space, because if you don't have that, sophisticated of a space or a program. So we go from model space, the model space, which is translated into the model and separated out by the model and the view transformations. When we take a look at the model and view transformations, by definition, these are the 3D transformations that simply change the coordinate system in which the triangles are defined. And we talked about this I believe in the last lecture. Talked about differences between rotation, translation, and the simple moving an object from one place in the coordinate system to another place in the coordinate system, which gives us that dynamic kind of evolving behavior. Not part of animation yet, but it's going to be eventually when we start looking at that. So the triangles are not actually moved. Actually, nothing is really moved. It's the rendering process of performing the transformation that's moving it. So we have the model coordinate space, the world coordinate space, and then we have the view coordinate space. As an example, if we were to model this room, for example, we'd have the floor, we'd have the ceiling, we'd have the world view. The model view would be a representation of the world in a smaller scale, more defined, but also more understandable scale. It would only include the components that we were interested in modeling. So we would pick out objects that we would include. The view is, as I was mentioning last time, is when we walk into a room. Like I have a facing view. Actually, you guys, you have a different view than I have. That's the view definition of the space that we're looking at. That's a model of the world that we're looking at. So those three components work together, and the transformations are calculated. so that we can view it. So here's the model to world transformations, and we actually looked at this last time. So each object is defined by its world, or RT, or its own model coordinate system that's inside of the world coordinate system. So this is one individual model here, object here, and the object has its own coordinate system. The object is put into the world, or into the space, and then the space has its own coordinate system. And then we have a view on the entire space that we can apply to that, as well as lighting models and different other components that we can apply to the space as well. So this is one world coordinate system for the entire scene, which is this red one here. And this is one object that has its own coordinate system inside of the world coordinate system. So it's a hierarchy of coordinate systems, long story short. And so this hierarchy of coordinate systems are all kept separately so that the objects can rotate and translate and move in the world system, and then the world system itself can move and be translated as well. And that's going to be determined by the view. The view is going to translate the world coordinate system. So transformations can be performed if one knows the position and the orientation of the world coordinate system and relative to the world coordinate system relative to the world coordinate system. Model coordinate system relative to the world coordinate system, as I'm saying this correctly 3 times. The model in relationship to the world gives us the ability to translate it. So you can perform it on the orientation for the world or for the model, or for them both together by using the model. World, not model. Okay, so transformations place all of the objects into the same coordinate system, the world coordinate system. So there's a different transformation for each object. An object can consist of many triangles. So if we broke this down even further, inside of here we have triangles or polygons that are coordinating in terms of this surface level. So we have the surface normal, we have the side surfaces, back surfaces that contain a subcategory or a separate hierarchy with more detail associated with the triangles and how they're defined inside of that space. So the world to the view transformation. So once all the triangles are defined, the world in the world coordinate system, we need to transform them into the view space. The view space, I don't have this in, here it is actually, here's the world, I'm going to flip back to it, is the camera view. So some people refer to it as the camera, but it's the orientation for where you're looking. Are you looking behind, in front? In fact, another classic example of the view space would be your view versus my view. We have 2 separate view spaces. You're seeing the room from a different angle than I'm seeing it from. It's actually the exact opposite angle. So if we had an image or an object in front of us, I'd be looking at the back side, you'd be looking at the front side, or vice versa, depending upon how we oriented the view and defined the view. So the view gives us our relationships of all of the angles in terms of what's facing forward, what's facing back, and what's facing the side. So the view space is defined by the coordinate system of the virtual camera. I have to imagine a camera in here looking at this stuff. Camera is placed using world space coordinates. And there's one transformation from world to view, so we have the space for all of the triangles if only one camera. So add another camera, and then you have multiple views. And then you can switch between the multiple views, and then you have some really interesting graphics going on. And some really heavy-duty, intense processing going on. And then the pipeline makes more sense because you're rendering the view given the camera position, and then you're flipping back and forth between the cameras, and then you have a pretty interesting, a lot of data, actually, a lot of data associated with that. But it's a pretty interesting kind of contrast that you can make and really create a 3D kind of environment. And what are you doing there? Well, you're not only moving the objects, but you're moving the view. So you're seeing it from different angles, as well as seeing the objects themselves. The objects themselves are changing their view orientation. So the camera's film is parallel to the view of the XY plane. So it's headed at the origin normally. By default, we consider that the normal position. It's the front-facing view. The camera points down the negative view on the Z-axis. So it's pointing down this way. So at least for the right-hand OpenGL coordinate system, things are opposite for the left-hand DirectX system. So this concept is associated with our graphic processing systems. Our VRML is going to follow the OpenGL format. DirectX is going to follow a different format. So our packages themselves, when we start using these graphic packages, are working with this concept, and they're both going to, everything's going to set defaults that are going to be particular to the orientation that's going to be set for the view transformation for whatever package you're using. You can change it, and you should be able to change it in almost any package, because that's really going to determine how your scene is going to look. So placing the camera in OpenGL and also VRML, default view coordinate system is identical to the world coordinate system, which means that by default you're seeing it straight on by the x and y intercept at 0. And the z, you're facing down the z-axis essentially. Camera's lens points down the negative z-axis. So there are several ways to move the view from its default position, and you would use library calls to change the cameras. The same thing you're doing with the rotation and the transformations, but you're looking at the view, not the objects. So last time we looked at object transformations and rotations. In fact, we looked at this in VRML, where we created a shape, and then we translated the shape, or then we rotated the shape. Same concept, but you're doing it on the world coordinate system instead of the object coordinate system. So the rotation and the translations can be performed to place the view coordinate system anywhere in the world. So you can turn the view coordinate system at different angles to affect your scene. So higher level functions can be used to place the camera at exact positions. We get that with OpenGL, and we get that with glue look at, which is an OpenGL command that says, here's an eye point, the center point up, and it uses up vector, and you can place a little bit more control over it, which is why people like OpenGL, actually, because we have the finer details that we can set for placing a camera, for defining a view. We have more control. In VRML, we could just ignore it completely and let the plugin control the view. And when you change the controls on the plugins and you're using that, you're controlling the world view. That's essentially what you're doing. But you can also do it programmatically by creating a view component or camera component, and then it's basically another object that you're putting into the scene in which you're setting some orientation for the entire view. So similar functions available also in DirectX. If you're familiar with that package. We have the transformation order to consider. We also have other things to consider I'm going to get into eventually here, but the biggest thing we have to think about is what's going to be shown first, which means what's in front of what that's viewable to the camera, or excuse me, viewable to the scene, or the model. It's going to show up on your display. What do we have to render, what do we don't have to render? And then what order are we going to translate things in? The translation order is going to give us nothing more than the appearance of something moving without jitterness, without weirdness. We want to get realism out of it. So in terms of the pipeline and the way that translation is done, there's been a lot of research and a lot of different algorithms that are created to provide faster, better translation and transformations in different orders to come up with different effects. So note that the order of the transformation is important. Points move from model space to world space, then from world space to view or camera space. The order is going to give us flickering, no flickering. It's going to give us, it's the order in which we're painting, if you want to think of it that way, but it's really not painting, it's transforming. Well, when it has how do you know when it's been transformed? Well, it's been painted, it's visible. So usually you're going to do the front surface first and you're going to do the back later. Non-visible, you're going to cut out completely. It's not shown. So in order to do that, you pre-calculate what's going to be visible, and that transformation occurs at that order first. So if one object's in front of another object, that one will always be transformed first. So closer to the perspective of the camera in terms of its view. So you can do distance algorithms. You can also play around with, and there's algorithms that you can actually set priority for certain things. So this implies an order. So the P view, the transformation view, is a the translation to view, world to view, times the translation from the model to the world plus the model. It's going to give us our view. So the model to the world transformation needs to be applied first to the point. So it'll start from the centermost point and work outward, or it can start from the camera angle point and work outward. So world to view details. Just to give you a taste of what goes on behind the scenes, and this is the glue look at is the method call for OpenGL that is the underlining same method call that you're using in VRML. But you have more control over it in OpenGL. But long story short, underneath there's algorithms that are being performed. So it needs to form a 4x4 matrix that transforms the world coordinate system into the view coordinate points. Same thing that we saw for object rotation. Create a matrix, do a calculation on it to rotate it left, right, up, down, by adding or subtracting coordinate systems one to another, and you can, essentially provide that kind of transformation to the world, which is what you're doing essentially. So to do this simply forms a matrix that represents a series of transformation steps that get the camera coordinate system to line up with the world system and do it in the order that's closest to the camera, because everything else will overlap. How to do that? What would the steps be if you had to implement the function in an API? Very difficult. This is where a lot of the time comes into the efficiency or lack of efficiency in terms of the rendering process. Tons of calculations, especially if you have a complicated world. Depending upon how many objects you have in there, you have to go through the coordinate systems of all of them in relationship with the world, and then figure out what one is going to be first, depending upon the current camera angle. So it's a lot of processing, long story short, which is why, going back to the original comment, which is why putting it in hardware, it makes it a lot faster. Because that can just take it in, perform the calculation automatically, preset the transformations, and then specify the order, and put it in a table or something, so the data structure itself can be kept right there along with the processing. So then we have view space. So there are several different operations that take place in the view space coordinate system. Backface culling, I'm going to talk about that today. View volume clipping, and lighting. So in terms of the rendering process, after you're familiar with all of the different objects that are in there, all of the different world components as a whole that need to be calculated, last thing in the world you want to do is do everything. If you're the graphics system, you don't want to have to process everything. So you're going to take shortcuts. How are you going to take shortcuts? Well, you're going to get rid of backfaces that don't show. Why render it if it's not in the site, if it's not in the camera view? Or view volume. You've zoomed in. The world is this big, but the camera is at a view angle that only hits a certain percentage or a certain part of the particular big subview. You haven't zoomed out yet. Wait, render it when you're ready to zoom out. Don't render it right now. It's available, but the volume is going to be clipped. So you're only looking at what the camera can actually see, and you're getting rid of all the other details. Or the last point, the lighting. If it's dark, it's dark. Why render it? You can't see it. So you render for the light source. And you go, well, what is visible in this particular view? If you're not using a light source, you can't use that technique. If you don't have any back faces, well, you're always going to have back faces, but you can turn on and off back face rendering. Volume clipping happens automatically for you, because that's going to essentially be the definition of your space in terms of your view coordinates. So note that the view space is still a 3D coordinate system. Although you're looking at 2 dimensions, you'll have all of the 3D information with you and available to you. So what ends up happening is you get rid of the 3D stuff you're not really using. The back faces, the coordinates that are outside of the view plane that you don't necessarily need to render. So you're basically reducing your rendering. So here's backface culling. Backface culling removes triangles that are not facing the viewer. It's the back. If I were to apply this technique to you guys right now, none of you guys would all have hollow backs. I can't see it. I can just see your faces and your bodies. I don't see what's behind. In fact, I don't actually see what's behind you from the next person in the front. Because this person is sitting in front of that person, you're blocking out a portion of her front side as well. I don't have to see that either. But traditionally, the concept works with the back of the object, not necessarily what's overlapping. Because you can take it a step further and apply a view clipping to it and get rid of that as well. That would be a separate, but backface is what's not visible, which is typically in a three-dimensional plane, it's going to be the Z. You're only going to see what's facing on a two-dimension. So it's actually a pretty easy thing to implement if you're the graphic renderer, because you know what the 2D plane coordinates are. You just get rid of the 3D components, so you can't rotate. So what ends up happening when you apply this technique is it makes it bad for animation. Because every time you move the object, you got to go find the information that's supposed to be there and populate it, which might make it move slowly. In fact, you see this with games when the guy turns around and he looks hollow for a second, but then he fills in, like automatically. And if it's done with the OpenGL, it's because, well, they had some backface culling going on. They rotated it, and the graphics processor couldn't catch up fast enough, so it didn't fill it in, didn't render it fast enough. And so you see that little hollow back end. Everyone's seen a hollow back end eventually. If you haven't, you'll see one eventually. If you play video games that use OpenGL libraries, if you turn that on, yeah, faster animation, but the rendering is still going through the pipeline and it still hasn't rendered the back yet, so it's missing. Which is kind of weird. Normal extends off the front face. So we have what we call it the normal face, which is the open-facing object that's always rendered. So our surface normal is what's visible and what's facing us in a two-dimensional plane. So the default is to assume that triangles are defined counterclockwise in terms of the object rendering. At least this is the default for the high-end coordinate system for OpenGL, does it counterclockwise. Some more sophisticated graphic packages, you can actually specify which direction you're going to render it in. DirectX's left-handed coordinate system is backwards, so it has front face, so the CW is front-facing. Clockwise is front instead of counterclockwise. So it depends on the graphics package as to which direction you're going to render in. And so when we look at this, this is the normal perspective is this way, if we're looking at this from a coordinate system. So here's our surface normal by definition. The surface normal, what is it? That each triangle has a single surface normal. So the normal is perpendicular to the plane of the triangle. Easy way to define the orientation of the surface, which is going to be the showing surface. Again, the normal is just a vector, no positions associated with it. It's just the open-faced surface that is exposed, given the plane, the perpendicular plane. So the normal is perpendicular. So think of the normal as the top of a table in terms of the perpendicular orientation of the triangle plane. So it's usually the facing. So computing the surface normal. So we don't have to do this luckily because we have graphics processors that do this for us. If we can compute, let's say V1, vertex 1 is a vertex from point A to B, and then we choose the vertex from A to C, so A to B, A to C. Then we can calculate the normal, but the space between them, so n is often normalized. When you say normalize the image, you're bringing it so the surface normal is facing. So the orientation is changed so it's perpendicular. And note that the order of the vertices becomes important. So triangle ABC has an outward facing normal, triangle ACB has an inward facing normal. So depending upon how you're ordering the vertices of the triangle, it could be facing out or it could be facing in. One of them you're defining as the surface normal, which is going to be the view orientation that you're looking for. So just imagine walking around in a circle around an object. It has two faces. Depending upon how, if you're reading left to right or right to left, or the order in which you're reading verses, you're going to be looking at this part, or you're going to be looking at this part of it, which is going to give us our two, but we're going to call one of them by default, depending upon the order that we set. That's where this comes into place. That's where this counterclockwise or clockwise is going to define our surface normals. Because if we're going counterclockwise, then the image itself is going to be facing this way. Or if it's going to be clockwise, it's going to be facing this way. We need that to know the painting sequence, to know what's visible, what's in the back, and what's in the front. So it just gives us our orientation. These are defaults that can normally be set manually in terms of parameters or properties that you can set on the world coordinate system. Usually it's going to be followed, like DirectX is going to use something, OpenGL is going to use something that's going to be set, and you just follow along with the format the package is going to set. Why does it need to define that? Because everything is in relationship to the way that the scene is being read. Because the rendering process is going to render it in the particular order that's given by the coordinate system. That's preset. So it means things are going to be behind are going to be called behind, or things are going to be in front are going to be oriented in front, given how you're reading the angles. So it's actually kind of an important concept. Most people don't really think about it because they're not going down to that level. If you're using a higher level API and you're dragging it on there, you go, oh look, it's facing the wrong way. And you just turn it around. Oh look, now it's facing the right way. But you just changed the orientation in terms of whether it was clockwise or counterclockwise oriented. So lucky for you, we're not going to go through all these different algorithms and techniques because we don't have to do this. In VRML, backface culling is done for you automatically. In fact, there's no way of even adjusting it. You have it, whether you want it or not. In OpenGL, you can turn it on and off. You can also adjust it, and you can also play around with which scenes and which objects you're going to apply it to. But the rendering system itself, depending upon what you're using it in, if it's at a higher level API, you still don't have any control over it. But as a concept, if you recall it, if both vertices are the unit vectors, it simplifies the calculation, and the dot product of the view of the polygon normal is the positive way of looking at it from the normal. So if you create the normal perspective, then the backface culling is going to be the reverse of it. If you take the 90-degree reverse. So you're just rotating it, essentially rotating it around the y-axis to figure out what the back is, and then you just don't render it. So the technique should remove approximately half of the triangles in the typical scene at a very early stage in the pipeline. Because immediately you're not going to, depending upon the view and the model space and the way it's defined, you're never going to see it. So remove it, which is a step you take, essentially the pipeline takes to essentially render it faster. We always want to dump data as early as possible because we don't want to use calculations on it. So if you can get rid of it to begin with, then that's why it's a nice feature to have in terms of the compilation. So the dot products are really fast to compute because you're only considering the facing. Can be optimized further because all that is necessary is the sign of the dot product. So the dot product is the point in which you're using as a reference. Everything ahead of the point is viewable. Everything behind the dot is clipped. Or shouldn't use the word clipped, it's called. It's removed from the data that's being calculated. So when you're using an API such as OpenGL or DirectX, there's a toggle for an on and off backface culling. You do not have a toggle in VRML. However, some of the browser plugins do have toggles and do have settings that you can set. But I have yet to play around with them. The Cosmo player doesn't allow you to do it. Everything is turned on because we're going to assume you're going to want to use the best presentation. The reason why you would want to turn it off is if you're creating a heavy-duty animation and you wanted it to all render ahead of time because you're going to quickly rotate the object. And you don't want the object to appear hollow. Then you turn it on. Because you have already rendered and you already have that information available to you when the scene is painted. So your animation is going to run faster. It's going to run smoother and faster, and you're not going to get those imperfections that you would normally see if you had it turned off. If you're not going to animate it, you're not going to move, or you're going to animate it very slowly, no need. It'll run faster without it. With it turned on. So there's also a toggle for selecting which side is considered the front side of the triangle. So the side with the normal or the other sides. So you can select if you're opening up the scene and you're behind and you're looking at something, then you can definitely reverse it so that you can select that the objects are in reverse. And if the objects are in reverse order, then your backs are going to be different. Your surface normals are going to be the exact opposite. So they're going to be the negative of what they were before. So it's a toggle that turns it on and off so you can switch it. View volume clipping. So I was mentioning before, if it's not in sight, don't paint it. So the view volume clipping removes triangles that are not in the camera's sight. The camera can't see them. So because you're zoomed in, or because you're only looking here, you haven't moved the camera over here yet. So you're only going to get the view volume that's in the camera, and you're going to clip everything else because you don't need it. What's that going to do? It's going to give you odd, if you turn it on and you're using it by default, which is what you're getting in OpenGL and also in VRML, then when you move the camera too quickly, depending upon the scene, it hesitates. The camera doesn't move. Because you have to stop and you have to render the entire scene again. And once you render the entire scene again and then switch the camera, you have slow movement. You don't necessarily have missing anything, but you have very slow camera movement, which causes real-time camera angling and walkthroughs are not possible. You can't do a walkthrough kind of simulation of orientation from room to room without, you turn view clipping off if you can, and so it's going to render. It's going to render the whole thing slower, but the movement's going to be faster. So, in general, the view volume of a perspective camera is a 3D shape that looks like a pyramid with its top cut off, called the frustum. So a pyramid, we've seen it actually in a different picture. I'm not sure if I have one in here. Oh, I do. Here it is. Here's the picture. So it's a pyramid, the top cut off, because we can't see the top. And what we're looking at is the view from the camera. That's why I say when you view it in and you're looking at something that's narrow, you're cutting off the rest of it. So here's the frustum here, which is the area for which we're defining our coordinate system within the view. Here's the far clip plane, which is we're just going to cut it off. We can't see it. Our viewing volume is going to come up to here. Anything past here is going to be gone. So we're not going to worry about that. Which is kind of, believe it or not, it's kind of like what our eyes do. When we look down something, we look down an alley, we only see to a certain point, depending upon our distance view, and then everything else is clipped away. We don't get that information. When we walk closer, then it gets repainted. And we see, oh, what is that? What is that? What is that? And we see more detail as we move in. So this is what the human eye actually sort of does, or the brain does, I should say. So the frustum, so thus the step is sometimes called frustum clipping, where that word comes from. Frustum is defined by the near and far clipping planes, as well as the field of view. So the frustum is a term to define what's viewable, what isn't viewable, and how we're going to clip. So the frustum clipping is the removal of the non-viewable components that are part of the scene that are in the model. More information on this later. We'll talk about projections, because projections actually play a part in this as well. So here's our camera. Here's our aspect ratio, our width over our height. Once we set the aspect ratio, then we get our clipping plane. And we have our near and our far. We go to the far to a certain point, we can set the far. So sophisticated software will allow you to set the far clipping plane. And so you can adjust what's visible and what's not. Because then if you adjust it too close, then you have things that should be visible that aren't visible. So it's kind of an interesting phenomena that occurs. If you don't have a background, or if you set a background, well, if you don't have one, you're not going to be able to see very much. It's going to be whatever empty, whatever happens to be back there. So view volume clipping happens automatically in OpenGL and DirectX, and it also happens automatically in VRML. So you need to be aware of it because it's easy to get black scenes, because you set your view volume to be the wrong size. What's your black scene? Well, it's too far away, so it's clipped away. So if this is too big, the view volume, is too small, then it's going to cut off at a certain point, and it's going to be black. That's why I say if you don't have anything back there, it's not going to show anything. And if you don't have anything, and you've got you're using a view clipping, and your view is set too narrow or set incorrectly, you're going to pretty much have a black screen. You're not going to be able to see anything. So you have to change the view orientation in order to actually see anything in the plane. Which is why, I believe in one of the examples there was the view orientation was clipped, and all you can see is water. But you can't see the fish in there. It depends on how far away you are from the fish. Eventually, you're not going to see the fish. Or if you come up close enough, the fish are going to be behind you. You're going to just see the water. So it's going to clip off everything else. Okay, also for some game speed up techniques, you'll need to perform some view volume clipping by hand in the software. Actually, by moving camera, by changing the view and calculating a view animation, then you can essentially speed up the process by manually stepping away from or stepping forward to and repainting, or I shouldn't say repainting, re-identifying the view plane. The graphics rendering process is going to repaint it for you. So you're just defining the view, and you're defining what's visible. Lighting. So as another concept, we have lighting to consider. The easiest form of lighting is to just assign a color to each vertex. If you assign a color to a vertex, then the lighting is going to cast some sort of it's hopefully going to merge together. Again, color is a state machine type of thing. Color is actually giving us, in some cases, it's going to give us the amount of illumination that's going to appear. More realistic forms of lighting involve calculating color value based on simulated physics. We also have in some libraries higher level APIs that give us what's called light sources. And the light sources are going to give us effects, pinpoint light, ambient light, different types of light and effects, and it's all associated with coloring actually. And here they are, real world lighting. So photons emanate from light sources, and the photons collide with surfaces. And they are absorbed, reflected, or transmitted. So usually on a shiny object, you make it shiny by reflecting the light. So you apply a reflection light. And luckily for you, in VRML, when you add a light source, you're giving it a property. You're just saying absorb. When you throw light on something and it's going to be absorbed, this is actually absorbed. There's no reflection. There's no transmitted. It's not sent to something else. This might be light coming from another. Well, this could be light that's being reflected off of another object. It's not being absorbed. Could be reflected. For the most part, it might be transmitted. So it's hard to tell unless you actually kind of look at the geometry of what's going on with the other components, the other objects that are in the world space. So eventually some of the photons make it to your eyes, enabling you to see it. So light provides illumination. So in terms of illumination models, the back that's not light doesn't have to be rendered. We can cut that off completely. Because it's black. We're not going to see it. Which is kind of interesting. So lighting, if done correctly, is automatically calculated from a particular starting origin out to as far as it can be seen. And then there's algorithms that determine which objects should be illuminated, which ones should be reflecting. And then we get into the concept of ray tracing. So ray tracing takes light and follows it from point A to point B, the furthest distance, and traces its natural illumination object to object, so we can create realistic looking shadows, realistic looking bouncing of light from one source to another source, and all sorts of different natural real world effects that might come out of that. So lighting models here. There are different ways to model real world lighting inside of a computer. We have the local reflection models that we get in OpenGL. Anything in here that says OpenGL is VRML as well, by the way. I know I keep repeating that, but just in case, I'm pretty tired of saying it's the same thing over and over again. So just OpenGL is VRML. It's built on top of OpenGL. Right. VRML is built on top of it. Okay, so global illumination models, that's where ray tracing comes into place. And I just kind of described ray tracing, but I'm going to get into a little bit more detail. In fact, we have an entire lecture on ray tracing. And ray tracing is one of those things that hasn't been perfected yet. In fact, even OpenGL doesn't have a proper ray tracing algorithm. There's a couple of third-party ray tracers that are out there that provide really nice illumination models, but they're not perfect. Ray tracing itself is a lot of calculation. You'd have to take the entire room, in this particular example, for ray tracing, and calculate the illumination that this ambient light is giving us, for the most part, if we consider it what kind of light source it is, and how it's reflecting light on each one of the objects that's in the room. And then we'd have to, figure out how to cast the illumination and then cast a shadow, or cast darkness, depending upon what's lit and what's not lit. So that's the complexity that you have in terms of all the calculations that are associated with ray tracing. So we have some global illumination models with ray tracing and radiosity, which I'm going to talk about a little bit later as well. So local reflection models calculate the reflected light intensity from a point on a surface on an object using only direct illumination. So this is a reflection from a point, so as if the object was alone in the scene. So we take the reflection model and we say if we're going to send it on this object, we're going to find the origin or the point, not really the origin, I shouldn't say that, the point on the object that we're going to cast the light to, and then there's an algorithm that reflects it. And reflects it from a particular diameter around the point that's pre-specified by the routine to cast light outward. It doesn't necessarily cast anything on any other object, or doesn't necessarily produce shadows or anything either. So some important artifacts not taken into account by the reflection models are shadows from other objects. We don't take that into consideration. Also inter-object reflection and refraction. So as a local reflection model, it's not used in large scenes with many components. It's used for simple things, such as the teapot example. You're just reflecting light off of a shiny object. So you're going to use multiple lighting techniques in the same model, actually, to get more realistic effect. So we have an extension on the local reference model called the Pong. You can never say that correctly. There's three different types of lighting that are considered, and this is what I was talking about before with ambient. Well, we also have specular and we have diffuse lighting. So if we define it out, this is one guy, this is his last name, and I can't remember his first name right now, but came out with his lighting model. It's pretty universally used these days. This is from the 1970s, I believe. So it's pretty standard. Nothing else has really come out. But his definition was the characteristics associated, and he defined these three types of light. And they're combined into color for a surface at a point of question to create different artifacts or different experiences for the lighting. So diffuse. So diffuse reflection. And here's the interesting thing. So to make this a little bit simpler in terms of what you're looking at, you don't get a choice of whether you're using ray tracing or radiosity. The technique for the light application is dependent on the API you're using. So OpenGL, Direct 3D, of the VRML are all going to select this for you. None of them are using ray tracing. The lighting models themselves, in terms of real-world lighting, fall under the categories of absorbed, reflected, and transmitted types of lights. The APIs define the three categories in terms of the models that are put together. This particular model defines diffuse, specular, and ambient. This is what we get in most of the general OpenGL and most of the VRML modelings. So we say light source, and we say for property diffuse, yes. Ambient, no. Ambient, yes. When we turn on and off these properties, these are what the properties, what I'm describing to you is what the properties actually do. So diffuse. Diffuse reflection is what happens when the light bounces off a matte surface. How do we know the surface is matte? We're creating the illusion of the matte surface when we apply the diffuse light to it. So it bounces off, so perfect diffuse reflection is when the light reflects in all directions. So we don't have a shininess, we don't have a single point. So on a shininess, we have the point that's detected of the light source that meets the object, and it's the brightest point. And the reflection on that goes off in one direction. In a diffuse, there's no center origin for the light source. Instead, it's all over the entire surface itself. Illuminates, and you can see the matteness of the surface. There's not very much reflection off of it. But we can tell there's a light source, usually achieved through a color change on the surface. So it's a lightening of the color change. So when we apply the light source and the type of light that we're going to do, so we have pinpoint lights, we have different types of light sources, and then we have different types of effects that the light hits the objects with. On a diffuse, we can't really tell, and this is a nice little example here. The light bulb that's turned on that's hitting the source on the surface, it's hitting it everywhere. We can't really find a single source of where it's bouncing, and there's no bounce really. So it's perfect diffuse reflections when the light reflects in all directions, and there's no single one point. So we don't actually cast rays from the light source and scatter them in all directions, hoping one of them will hit the camera. So this technique is not very efficient. So even offline techniques such as radiosity, which try to simulate diffuse lighting, don't go this far. Better to use color. We just need to know the amount of light falling on a particular surface point, and then we illuminate it. So it doesn't provide very much of an effect. We don't get very much out of it. So the amount of light that's reflected, the brightness of the surface of the point, is proportional to the angle between the surface normal, N, and the direction of the light, or L. So that's going to give us our radius, if we're going to use a radius calculation for this, for what's going to be illuminated. And it's going to be a calculation determining the distance between the light source and the surface normal. So it's kind of like the same effect you get with a flashlight. You can calculate it really easily. Go farther or farther away, and the circle gets bigger, the light gets bigger. So it's the same kind of calculation that's performed. So the resulting diffuse intensity, I, is the incident intensity, and the NL unit vectors. So that's the calculation between the distance of the light to the surface normal. And a couple of examples here. I'm not going to go through the examples. You can just do the examples real time yourself with a flashlight. Walk closer or farther away, the farther away the distance, the bigger the light actually gets. And the less intense. Closer to the surface, the more intense the light, the brighter the light, the smaller the circle. So here's our diffuse examples, and these are OpenGL examples, by the way. So the diffuse is coming from this angle on the light source. Diffuse reflection only depends on the orientation of the surface. The position of the light does not depend on the viewing position. Our viewing position is this way. We're heading on this. Can you see that? A little bit. It's a little darker on your screen. There's like a red ball in here. And a piece of the red ball that's illuminated is coming from a light source that's on, well, if you're facing the image, it looks like it's coming from right behind it. On the right upper behind is where the light source is coming from. It's not head-on with the view plane. If it was, we'd see a red ball correctly in front of us. So the bottom sphere here is viewed from a slightly lower position than the top sphere. It is, actually. This is up here. In fact, you can see it because you probably can't see it in here, but there's a little bit lighter illumination going on here. And then this one is a little lower, actually, so you can kind of see the light source move. This gives us your realism. So you see your diffuse lighting kind of absorbs in a circular fashion on the object itself. So. Specular lights are the mirror-like reflections found on shiny metals and plastics. Well, anything that shines is going to give us specular. So you can create a shiny surface. This is not shiny. Well, there's a better picture back here somewhere. No, there's no better picture, I guess. That's not too shiny, that's shiny. So the way you make it look shiny is you cast a specular light on it. And then it looks shiny because the light's illuminating it in kind of a shiny format. So the surface normal, N is again the normal of the surface at the point where we are illuminating. L is again the direction of the light source. We're still taking that in consideration. R is a reflective vector. And V is the direction of the view, the camera. So if you were doing this in OpenGL, you would say specular light, and you would specify the N, the L, the R, and the V by coordinates. So there would be numbers associated with them that would match up with the coordinate system that would tell you, here's where it's coming from, here's where it's going to, this is the surface normal it's hitting, and, long story short, this is the effect that we're going to achieve from this combination. So you want the intensity to be the greatest in the direction of the reflection vector and fall off quite fast around the reflection vector. So we have intensity is higher in the beginning, at the center of where we're going to hit the normal, and then it falls off and it kind of tapers. So we have a shininess kind of, it doesn't break off completely. What makes it look fake sometimes is when you see light, it's a circle, and it doesn't fade into darkness. It just sits there. So cheaper graphic programs, you put light on something, the whole thing is lit up. Not very realistic. Or you don't see the light shading correctly or tapering off correctly. So you have algorithms to actually taper it off correctly. So let's see. So as N gets bigger and it drops off, the R is faster dropping off. So as you get farther away from this surface normal starting position, the rate in which you're dropping off increases so that it gets dark real fast. Because shininess is kind of more strong in terms of this direct effect, and it tapers off faster. So here's some examples of specular lighting here, the examples of various different values of N. So the light, on the left we have diffuse only. So this is diffused. So you can see that these aren't actually shiny at all. The light source apparently seems to be the same for all of them. The middle is a low N specular added to diffuse, which means it's not going too far. The right is a high N specular added to a diffuse, so we actually have pretty interesting effects depending upon how we're specifying the intensity. So whether it's a low specular or a high specular, all being used with diffuse lighting. So we're combining the techniques to actually give us an effect. So which one's the best? It depends on what you're trying to do, what you're trying to show. So if this were the sun shining on something, not very realistic. This would be more realistic for a sun, actually, I think. So calculations of the N, the V, and the L are easy. The N with the cross product of the triangle vertices. The V and the L are the surface points and the camera, the light position, respectively. And you calculate the R required by mirroring the L about the N, and requires a bit of geometry. It's just a simple calculation. Lucky for you, you don't have to do any of this. In fact, in OpenGL, you don't have to do any of this. You just run a light source, and you say specular, diffuse, ambient, and you specify out where is it going to hit it, and how intense do you want it, low, medium, or high, and it's done for you automatically. But if you were to write the API, if you're going to look at it from a low-level implementation, these are the concepts that are being used for it. So in terms of the specular, the reflection vector R is time-consuming to compute, so often it's approximated by a halfway vector. Yes, there's definitely shortcuts and approximations that are being taken in order to achieve this, because otherwise, does it really matter if you have it perfect? No. In fact, it's more realistic when it's not perfect and you have some imperfections in it, because then it looks more realistic. If all of the objects casted the same kind of light source the same way, they were at the same distances, that would look very unrealistic. But if you approximated it and you tapered it off as the farther away you got from the light source, who knows when something is more shiny than something else. And it's the same phenomena that we're actually used to. So most people don't realize it, but sometimes when you walk into scenes, your eyes, your camera, Have you ever noticed something looks shinier than something else? It always catches your eye. Well, it's really shiny. That's an imperfection. But it wasn't created by the graphic environment. It was created by your viewing angle. Because the light was just hitting it. You know, it's like sometimes you see, like, when you walk up to cars in the middle of the afternoon, and you see, like, a really bright windshield or something, or really, you know, something is really illuminated. Something's sparkling, and it usually catches your eye because it's not normal. There's something wrong with it. It's an imperfection. We get the same thing with approximations in the graphic scene. So it actually is a good thing because it creates imperfections. It's approximations. So the real world's approximated as well. And the other interesting thing is, you know, our eyes don't actually pick up everything either. So it depends on your light intensity. Some people can't see the same type of level of light as other people can. So, especially after you've looked at computer screens for too long. It actually ruins your eyes, and you become, what do they call that, light blindness? You can't see light. Everything's dark. So, anyway, that's a different topic. Going back to specular here, specular lighting depends on the orientation of the surface. Where is the surface facing? Where's the surface normal? The position of the light, obviously, and the viewing position. Where are we going to view it? So the bottom picture is taken with a slightly lower viewing position. Yes, it has. It's behind, well, it's very low. The specular highlights changes when the camera moves. So if you have the world coordinate system defined correctly, and the object space defined correctly, and the light source position in the correct location, when the objects rotate, the reflection from the light source changes automatically too. That just adds more to the information to the graphic pipeline for you. So that's another piece of information that provides more time-consuming calculations. The more light sources you use, the more times you have to actually recalculate and re-render the object with applying the proper light source. So you're going to use whatever it is you need to use, but not an excessive level. There's some people that will put in light sources for no particular reason. You're just slowing down your rendering, because it has to be calculated for each one of the light sources. Ambient. I think that's what we have here. I'm not sure what we have in this room. It's kind of a combination, actually, because I see shadows being casted. It's not true ambient lighting. So now the previous example is that the part of the sphere not facing the light is completely black. We don't have to render it then. So in the real world light would bounce off of other objects, like the floor and the wall. And eventually some light would go and get back to the sphere. So we might be able to see the bottom part, depending upon what was underneath it. So the global bouncing is what the ambient component models. So the model is a very loose term here because it isn't at all close to what happens in the real world. It's a calculation. As an example, if we had something underneath this guy here, oops, wrong direction. If we had something underneath, we would see it. In fact, if you want to think of ambient as the total light, which is what it is, it's the calculation of all the reflective properties of the other objects in the scene added to the reflective properties that are being cast on the current object. So here's an example, and you can sort of see now, you can see the back part is not quite as black, it's a little bit more illuminated. So the amount of ambient light added to the point being hit is simply IA, and then note that it doesn't depend on the surface orientation, the light position, or the viewing direction. So that's why I say it's kind of like this room, sort of. We're illuminated, but I see everything. Well, hopefully I see everything. I see the floor here actually as well. The thing that's underneath the desks here are lighter in color, but I still see them. They're not black. So they should be black because the light's not casting. The light's not making it black because it's not being seen. So from local illumination models, the three components are reflective light that are combined to form the total reflective light. So we put these combinations together and we get different, in the model itself, we take these three different combinations, we put them together and we get different effects. So in OpenGL, the models are both based on Prong local model in illumination models. So it's based upon this model, so is VRML. So in OpenGL model, we also have what's called the light color. So we have incident light, represents the color of the light source. Blue light, red light, orange light. We have illumination that comes in color, not necessarily white. And then lighting calculations that determined. And now it has to be done 3 times each for each one of the color combinations, because we have those 3 that are coming into playing a part with the light source. So each color channel is calculated independently. And then further control is gained by defining the separate value for ambient, diffuse, and specular. So if you take the 3 combination characteristics and put them together, then you can define how much ambient do I want, how much diffuse, how much specular, and then what color is this going to be. Because, you know, the sun's not white. The sun's yellow. Is the sun yellow? I don't know. That's actually kind of an interesting philosophy. I haven't looked outside, but is the sun really white? I don't know. It's a good question. Well, headlights are white, but you can add color to it. The sun's actually not really. It's like an off-white, I think. No, white. You can tell because you look at the sky and you see white clouds. Maybe you see white on white. Well, white it's on blue. So anyway, kind of interesting color. We have the RGB scale that is defined for each one. So for each light source, you need to define the following colors: red, green, and blue for diffuse, for ambient, for specular. Ambient is used for the IA equation. One is used for the ID. One is used for the IS. It's basically the 3 components that are being put together. So we have material properties. Matte gives us matte looking, shininess looking, rough looking. So equations that compute it just compute how the light from the source is going to be reflecting upon the object. You can also define the color of the object in terms of the ambient, diffuse, and specular, which in this particular case is going to give us our matte looking finish, or our shining finish, or our dull. So in terms of the color model, the ambient light color is multiplied by the amount of reflection of the ambient lights. So if we casted a blue light, it's not necessarily going to be the same blue color that's going to be casted on each object, depending upon how close the object is to the light source. Anything closer is going to be darker, anything farther away is going to be lighter. So it's the same phenomenon that you get, especially, if you ever seen swimming pools with the light covers. And that's the other thing that most people might be familiar with. You swim up to the swimming pool, and the water itself changes color, and the water in the middle is white. And as you get closer to the perimeters where the lights are that are blue, it gets darker. That's the phenomenon that you can actually create using OpenGL, using VRML. Light up a swimming pool with a blue light or a red light. Or hot tubs have the same concept, but hot tubs are harder to see because it's a smaller space. So the light intensity is darker, so you're getting more lights. It's a smaller space. The theory with the big pools and what happens in nature, naturally, is that the more distance you have between the center origin of the pool and the light source, the lighter the color is, because the light's not casting there. So it's the same thing that's simulated. So OpenGL, actually, in these lighting models, are trying to simulate the real world to the best that they can, using algorithms with properties that are associated with real world phenomena that occurs. So similar processes for diffuse and specular. Then, just like in the prong model, they're all added together to produce the final product, or the final color. And note that each K and L are vectors of 3 color values, RGB, and they are computed independently. And as I was mentioning before, you're not going to memorize the RGB scale. You're going to go online and look it up. And say, what color is this? Well, there's an RGB number associated with it. So you're also going to define the shininess as well, so the material values that are used. In fact, you get this with VRML with higher level controls. So you say, I want it to be shiny, I want it to be flat. And you can actually create these sort of phenomena by setting properties in the object shapes. So by mixing the material colors with the lighting color, one can get a realistic light. So here we have a red light with a red material. And then we have a green light, same as the red material. But it's on a green material instead of a red material. So white light and a green light. Well, this is white in color. This is green in color. You can't see it probably because... Oh, actually you can see it. This looks kind of green. That's supposed to be white. White light with red material. Here's a green light with same red material. So it's green. You can see it on your screen. But also the point of the light is green. So. But it took and it created a green light on the red, made it green. So. And that's kind of intense, actually. So you can't see any of the original red underneath it. So something can be emissive. So OpenGL model also allows one to make objects emissive. Does that mean they look like they produce light themselves? They emit light. So if you wanted to create a light bulb, that would be emissive. So you created an object in OpenGL or in VRML, and you called it a light bulb. Actually, that might be an interesting test. It might be an interesting, not test, a project. Create a light bulb. And then you'd have to, well, that's be easy though. You just give it a really high emissive quality to it. You make it white, and you make a circle with a cylinder or a cone underneath it. You'd actually be able to make a light bulb pretty easily, actually. But if you think about, the old Pixar thing, people like to do this all the time, the little lamps, they put a round light bulb inside of it. It's just a circle. So you put a circle inside the thing and you move the arm around and it emits the light. Well, you're just casting a light source. The light source is casted from the camera angle of the bulb, and that's the starting position. And then it just moves around and casts lights throughout the room. It's actually pretty easy to do. It looks pretty fascinating, but somebody did that at a low level for Pixar. If you use OpenGL, if you use VRML, it's a little bit easier, actually. Okay, so emissive properties are put on objects themselves and make them glow. So extra light they produce isn't counted as an actual light as far as the lighting equations are concerned. They're just the properties are emissive for the object. They don't necessarily cast lights. They don't have to. That way you'd put a light source there if you wanted to cast the light. So emissive light values are simply added to the resulting reflective values. Then we have attenuation. So one can also specify how fast the light will fade as it travels away from the light source. You want a strong light bulb, or do you want a weak light bulb? It's your attenuations, because how far is the light going to project? Which is kind of interesting. So it's controlled by an attenuation equation, which is basically going to be how strong is the flashlight. Well, calculation is going to be the distance between, well, you're going to fix the distance, and you're going to fade the light to a particular distance, and that's going to give you the attenuation that you're going to achieve. So where the 3 Ks can be set to by the programmer, and the D represents the distance between the light source and the vertex in question, it's all fixed on the distance. So depending upon the distance, you're going to fade the light to that particular distance. So it'll be a faster fade if it's short, so, which makes it not very intense. The longer the distance, the more intense the light. The stronger the light's going to be for half the distance, and then it's going to fade for the rest of it. So the equation, so the total equation is going to be calculated from the RGB independently, and then each one of the light turned into the scene is going to be calculated, and then from the vertex in the scene as the origin is going to be calculated out to the distance point. So note that the above equation is slightly simplified. Yes, it is. I didn't even go through it. I'm not going to go through it because it's too simplified. You don't have to do it. If either of the dot products are negative, you use a 0. Spotlight effects is not included. Global ambient light is not included. It's basically just for projected light. So. Light sources. So I've been talking and I've been using the term light source, but I haven't really defined it. Here's your definition of light source. Depending upon the graphics package that you use, you're going to have a different light source available to you. Most popular ones give you certain effects that are most common in the real world. As an example, point lights. If I had those little red pointer things and presenter tools, that's a point light. You see the light reflected on a single point or a series of points around from a certain diameter, depending upon the intensity that we're setting, which is going to give us our attenuation. So those little things that drive cats crazy, and students, when you use them on presentations, go, hey, it's a point light. It's a low point. Then we have bigger point lights. Spotlights is a point light. So you're on a stage and you want to put a point light out there, that's a spotlight, a point light. Directional lights, that's the concept of the flashlight. You hold the flashlight out It's not a pin, it's not a point, it's directional though, in terms of the focus or wherever you're pointing the light to. It's a pointed light. Spotlights, same concept. Similar, they're giving a directional, but they're more intense, and they usually generally have, it's kind of like the receded lightings or spotlights. We don't have, these aren't really spotlights, these are more extended lights, but their spotlight would be one of those like little round receded lights you see in kitchens. Those are spotlights. They're bigger, they're not pointed, and they're not directional, they're fixed, so you can't move the direction. They're usually fixed. So, headlights in cars are spotlights. And then extended lights, which is just another form of ambient light, which is what these things are. They're big lights. They're extending from multiple different types put together to cause large illumination. Now we have the concept of projection. So there's not really too much to talk about light source. You just name the type of light you want. And depending upon the object that you're trying to, and I tried to give you some real-world examples. If I were creating a flashlight, or if I was creating a pointing device, or cars, headlights, I'd pick one of the different ones. Lights for the room, different kind of light sources. So projection is what takes the three-dimensional down into the 2 dimensions. So we see in 3-dimensional, which is kind of an interesting concept. We design in 3-dimensional. We view it in 2 dimensions. When we project, we get the 2-dimensional scene. That's how we're able to actually, and what we're looking at is we can't see everything. So our imagination fills it in on a 2-dimensional plane. So we know that there's a backside, but we can't see it. We know that there's sides of it, but the projection is giving us our facing view. That's what a projection is. So we can change the projection to render the scene differently. And that creates the, again, it transposed 3-dimensional to 2-dimensional where our minds can fill in the blanks in terms of what we're looking at. So there are several types of projections. We have orthographic or CAD. Perspectives, which is what we normally get in terms of camera angles, and that's the one I've been using for VRML. We changed the perspective. We've altered the projection. It's a perspective is a type of projection. And stereographic, which is the fisheye lens. This is what's in terms of a scope or a fisheye to change the projection. So we're zooming or we're specifying. Hello. There we go. Orthographic projections. So we have an equation that's calculated from an x position to an x position, or y position to a y position, and an image plane. It's pretty head-on. So the main property that is preserved is that the parallel lines of the 3-dimensional remain parallel in the 2-dimension. So the orthographic is the same. It's a parallel projection from 3 to 2. We only see what's visible in the 2. We don't see the 3rd, which is the most simplest, usually by default, in terms of the type of projection that's created. The perspective projection, and how this is equated into computer graphics, creates a foreshortening effect because it's from our perspective. If I'm standing over here, and we saw this actually in a previous lecture, if I'm standing over here and I see a chair and I see half of a wall, and then I change my perspective and I see the chair but no wall, it depends on what's going to be visible in the view plane depending upon your perspective, which is your camera angle, your camera position, which is going to give that to you. So you have the center projection that's going to give us your image plane that's going to specify what's visible. And so in this particular case, the rest of this isn't visible, only this little section right here is. Because you're looking up, or you're looking down. So it's just going to give you that. So the main property that is preserved is that the sight lines in the 3-dimensional remain sight in 2-dimensional. So are you going to use what's parallel from 3 to 2, or are you going to use what's visible from your perspective points? So projections in OpenGL also applies. It sets the projection matrix instead of the model view matrix. So you can set your projections and then rotate your projections. You can do this for creating animations where things are moving, and by adjusting the perspective. The camera can move or the objects can move. This is usually done for camera moving, so usually in the projections. So equations can be given previously can be turned into a 4x4 matrix form. What else would you expect? So yeah, everything's done in matrix forms. So you take the matrix and you translate them. And for the orthographic view, the view volume is the rectangle. So you use GL ortho for that, and you specify out the rectangle view plane. And perspective is the view volume is the frustum that we talked about earlier. So whatever happens to be parallel in terms of the view for whatever angle is supposed to be within the sight, and then everything else is clipped. So, and it's a different, and these are 3 different functions that are used depending upon which effect you're trying to get. So what do we have here? The calculation. So it's important to pick a good FOV. FOV, refresh my memory. Focus of view, forward of view. Image of the scene stays the same size. Distance between the, I can't remember what it's called right now, distance between the camera and the object. It's like level of detail, there's FOV. Bigger the FOV, the closer the center of the projection is to the image plane. The farther away, excuse me, the smaller it is, the farther away it is. So it's the, what in the world does the F stand for? It's of view, but I can't remember the F, the frustum of view. There we go. Hello. Okay, so I'm back. So frustum of view is giving us our view plane in terms of our definition of our frustum. So the bigger the frustum of view, closer the center of the projection is to the image plane. The smaller, the wider it is, the wider, the bigger, the closer everything is. The smaller, the farther everything is away. So it's, you ever seen those things where you've got, you look down a hallway and you see things get smaller and smaller and smaller and smaller? Well, it's farther away and it's a narrower view. The bigger the view, things actually look bigger. So that's phenomena is what's being described here. There's a calculation for it in order to make it realistic. So the human viewer needs to move their eye closer to the actual screen to keep the screen from being distorted as the FOV increases. Which means your line of sight, things will get smaller, so you're moving closer so that things get bigger again. It's the distance phenomena of the frustum and what's in the viewable plane. So I can think of it. So you pick a good frustum of view to put the actual size window on the screen. So you have a good starting point that's comfortable for viewing, for visibility, and you set a comfortable viewing distance. So basically, how far away are you standing from it? So that's going to be your FOV. And then you determine how much the window subtends as of your eye's viewing angle. How much of the window goes away, how small it gets. So method is effective if it places your eye at the center of the projection and will create the least distortion needed. So actually, you can tell the quality of some graphic packages and some images as to how clear things are, actually, the farther away they are. Really minimal, cheap graphic programs, things in the distance don't look so clear. Believe it or not, you get the same thing with cameras as well. The higher quality the camera, usually the better quality the image resolution is for distance. You see things a little bit less fuzzy in the background. Cheaper cameras, you know, you go and you focus on a point. It's great giving you your FOV actually at that point. And then everything else is everything's in focus here, and everything else is blurry everywhere else. Good cameras won't be blurry, would be nice. But your frustum of view is actually set with the camera, with the position that you're setting it at to begin with. You guys have used those digital cameras that do that? It's usually the new digital ones do that. You know, the snap and click ones. You have a little box in the middle and you set it, and then you click it once and it sets the focus, and then you click it again, it takes the picture. Yeah. It's basically setting the distortion that you're going to get from things farther away and where to put your focus point. It's setting your view, your FOV. Normalized device space. So this is our first 2D space that we're going to get from the 3D, and we're still following the graphic pipeline, by the way. We're getting towards the end of it, so don't worry. So what we're going to end up here is our first rendition of the 2D that comes from the 3D rendering. Although some of the 3D information is often kept because we need it, depending upon what technique we're turning on and off. The major operations that have happened in here, we have the 2D clipping that's going on, pixel shading, hidden surface removal, and then texture mapping that might be going on. So in terms of 2D clipping, when the 3D objects are clipped against the view volume triangles that are partially inside the volume were kept, the other ones are outside. In terms of the clipping, it's going to be taken away. So when these triangles make it to this stage, we have parts that hang outside of the window and they're clipped away. Because we can't see them, we might as well just get rid of them. In terms of pixel shading, what happens at this stage is the lighting equations that we have seen or we've looked about so far obtained by color, in particular vertexes are applied. So pixel shading is all about taking those colors and colorings of each pixels in the triangle and applying them. So there's three main methods for shading, for pixel shading. Flat shading, grund shading, and prong shading. Depends on the graphic package as to which options you're going to have available to you. OpenGL has all three of them as shading components. I have an entire lecture on shading that I'm going to give you, so I'm going to save those definitions. Not to be confused with the prong local reflective model previously discussed. This is a shading model made by the same guy that provides different properties and different settings to apply shading techniques. You think, well, what in the world is by shading techniques? And believe it or not, it's in here. Here we go. So just to give you, I have more information on shading, but just to give you kind of the roundabout summary of it. A single color, on a flat shading, a single color is computed as a triangle is at the center point of the triangle, and it's shaded outward, so using the normal of the triangle surface. You compute the color. The computed color is used to shade every pixel of the triangle uniformly. So flat shading just shades it, makes it uniformly among the entire surface normal. Produces images that clearly show underlying polygons. And here we go. We can see the underlying polygons in terms of the shading. This is our Pixar example, actually. So you can put a light source in there and shade it down. But this is shaded. You can see how the shading is applied, and we can see the distance. So in the ground shading, we have the three colors that are computed. Here we go. See, this is smoother. You can't see the underlining pixels in here. I don't know if you can see that in this on the screen now. So this kind of shading, you see it's good for this if you want to see the detail in the underlying polygon. It doesn't shade the vertexes, it just shades each one of the surface normals. So you can kind of see how it's kind of a little primitive, but it does provide a nice effect if you can see that. Actually, you can see this piece here in the description. So if you take the three colors and you compute it at the triangle and you find the vertex of each one of the colors and use the neighboring average normals, and then you take away the lines and you get a smoother shading that occurs. So what is the neighbor average normal? Well, that's an interesting calculation. You have to come up with a formula for that. So the average of the surface normals for all of the triangles that share this vertex. So you have to pretty much figure out who the neighbors are, come up with the average, and then shade it smoothly. Then you get rid of the transition points between the polygons. So the triangle model is approximating an analytical surface. Then the normals could be computed directly from the surface descriptions. I'll do this in the sphere example. The sphere example is actually coming up. In terms of its application with OpenGL and graphics libraries, you can use a bilinear interpopulation approach, which is used to shade the pixels themselves from the three vertex colors. So interpopulation happens with 2D. So the advantage of the ground shading has over the flat shading is that the underlying polygon structure can't be seen. So here's the problem with the ground shading that's on the left, is that the specular highlights don't interpopulate correctly. You can't see it, but you've got some interesting effects that are occurring with the population. So depends on you pick your neighbors. You might be able to see some of the interpolygon connections, and you can't see some of the other ones. So you'd actually have to put this on a computer screen actually in order to see it. I don't think you're going to be able to see it correctly on that projector. And our last model here, the prong model. Many colors are computed at the triangle. So you take many different center points. Instead of using a single point, you take many different ones, and then you can compute a flat, more evenly shaded model. So the back projections of each one of the pixels onto a from a three-dimensional triangle are used. using normals that have been bilinearly impopulated. So looking at it from a 2D perspective, the normals are at the 3D vertices. So you're making more points of the 3D vertices, calculating more center points to get a more even shading. So the normals of the 3 vertices are still computed as neighboring average. So you're using the same technique as the ground, but you're using it with more different starting points. So each pixel gets its own computed color. Advantages as the shading has over the other ones is that it allows the interior of the triangle to contain specular highlights. So the inside of each one of the polygons actually is considered instead of just the one single point. The disadvantage is that it's easily 4 to 5 times more expensive. Yeah, if you take one calculation and times it by every single polygon that's in the image, that's on the surface normal, then you end up with a lot more calculation. OpenGL does not support this type of shading, actually. And here's the shading here. You see it actually here. Where this is illuminated at the same. So actually you can't see the bottom, but it's shaded right here. Maybe you can see it. Well, you can see it a little bit if you look at that. The angle that I'm looking at that screen looks kind of weird. But this is an example of it. OpenGL doesn't support it, actually. VRML doesn't support it either. So, shading comparison examples. Here's our wireframe. Our flat, can you see this? Actually, you can see this. See, the flat is showing you the polygons. The ground is using an approximation of neighboring algorithms, neighboring polygons. And then the front down here, a little bit better, but I actually can't notice a difference on my screen. You probably can't see it on that projector either. Shading is one of those things where you have to be able to see more details in terms of the pixel quality, which makes it so that, you know, what's that expression? Dumb happiness? No. The stupider you are, the happier you are. Well, in computer graphics, it's the worse screen you have, the better your graphics look. In fact, it's the same for cameras, too. But the higher quality graphic monitor you have, the worse everything looks. Especially if it's not a high quality image. So, anyway, long story short, that was the comparison I was trying to make. So we have hidden surface removal. Let's see, hold on a second. Let me see where I am, because I think we're running a little bit low on time. Let's see, I'm slide 73. See, buffering. I don't want to get into any of the stuff. Okay, so what time is it? Oops. It is, it's time to end. I think we had enough for today. So, TA, remind me, I stopped on, which slide was that? 72. 72. I'm going to stop on 72 because what we're going to get into is texture mapping, and we're going to get into some more topics that I don't have the energy for right now. So, let's wait and do it next week. We got plenty of time. Alright, that's all for this week. Let's see if I can cut this here.